All right, let's get to work on the next one. And the next one looks like this. And you can't see it, but you're about to. So here goes. Let's try this one more time. It looks like this. There it is. Okay, we're going to be dealing with counting methods. This is permutations, combinations, fundamental counting principle, all the fun stuff. It's a lot of fun. You are actually going to need a graphing calculator, or we haven't done these on a calculator. You might need to go to one of the best websites ever, and it is this one. It is Desmos. Just plain desmos.com/calculator. That's what you're going to be using. I will use that. I might show you the calculator once, maybe twice, but overall, I will be using this. And this flowchart is going to help us more than anything else. So let's just jump in. A men's department store sells 3 different suit jackets, 7 different shirts, 8 different ties, 5 different pairs of pants. How many different suits consisting of a jacket, shirt, tie, and pants are possible? We're assuming everything matches, so let's just jump in. So we're going to have jackets, and we're going to have shirts, and we're going to have ties, and we're going to have pants. And we're going to multiply our options together. So here goes. Is there a large group put into a smaller group? No, actually, there's not. And you could be like, well, I'm only picking one of this and one of that. But when it's a large group put into a smaller group, you'll understand it in that context a little bit better. So just use the fundamental counting principle and multiply your options together. So I have 3 jackets, 7 shirts, 8 ties, and 5 pairs of pants. That's what's hanging in my closet right now. And just multiply your options together. There's a way to represent this differently, but we're not going to. So 3 times 7 times 8 times 5. Let's do it. I'm grabbing a calculator. 3 times 7 times 8 times 5. And I have 840. There are 840 different outfits that I could wear. Well, this is at the men's department store. All right, let's jump on to number 2. 6 people are running in a race. How many different orders can these 6 people finish? We are not putting a large group into a smaller group, so we're going to use the fundamental counting principle. So we could have first place, second place, third place, fourth place, fifth place, and sixth place. And here's the fun part. If we were picking first place, we have 6 people that could be first. We just picked the winner. Now we have 5, and then we have 4, and then we have 3, and then we have 2, and then we have 1. And we multiply our options together. And this is one of those that we can just know off the top of our head. It's 720. Some people know it off the top of their head. Some people don't. That's fine. If you really need to know this, and it's fun to know, this is actually 6 factorial, and that can be done in Desmos as well, also on the calculator. All right, number 3. 6 people are running in a race. Wait, same problem. No, it's not. How many different orders can the top 3 people finish? And we're going to assume that there is no tie. So we have first, we have second, and we have third. And this is one of the 2 ways we're going to do this one. We have 6 options for first place winner, 5 and then 4. So 6 times 5 times 4 is going to give me a number that I am ashamed that is not coming in my head right now, 240. There are 240 ways of doing this. However, there's another way of doing it. So let's kind of put this in a different context. 6 people running a race. I only want the top 3, and the order matters. Let's slide back up here to the top. Is there a large group put into a smaller group? Yes. Is the order of the small group important? Yes. We're going to use a permutation. We put the large number first. So in a permutation, we would put, now this is the way it looks in Desmos. It would look, I'll write it in red, in PR, and then big number, a little number, and we'll do that. And we would get 240. If you're going to use a calculator, and I'm just going to show you this one once because some people prefer this, some people don't. If you press the math button, and you can go over to prob for probability. This is somewhat of a probability thing. We can go down to NPR, and the big number comes first, the little number comes second, and it's 120, which means that I have done this problem wrong. It is not 240, it's 120, and I'm deeply ashamed of myself, but I'm not going to start this video over because I have been trying to do way too much in my head at the end of a very long day. So, if you will forgive me for an egregious math error, the answer is 120. 6 times 5 times 4 is 120. This is 120 no matter where I type it and what I do, unless you're doing it wrong in your head like I did. All right, here goes. Number 4, 10 students in a classroom and the teacher needs 3 volunteers. Whoa, now, hold up. Big group put into a smaller group? Yes. Let's keep reading. How many different groups of volunteers? They never ranked the volunteers. They were never like, okay, you're the supreme volunteer and you're second volunteer. So this is a combination. We're going to put the large number first. So I don't have a whole bunch of writing on this one. I'm just going to write it the way I would type it in my computer or calculator. In CR for combination, 10 students. I need 3. Let's go to Desmos. Here it goes. Desmos.com/calculator, and you can actually type it this way, in CR, and that's the notation that a lot of older textbooks use. I say older because with the advent of technology the way it is, things are a little bit different now, but NCR 10, 3, and it gives us an answer of 120. Coincidentally, is the exact same answer we got on the last problem, assuming we did the last problem correctly, which I did not. So I'm writing my answer on my paper. You can't see what I'm writing, but that's okay. 120 different groups of volunteers are possible, but if you don't remember how to type all that, that's fine. Just follow me here. Let me get my face out of the way. There we go. This floating head in the middle of my work. Click down here where it says Show Keypad, and where it says Functions. We'll click Functions, and I will scroll down. I think it's all the way at the bottom. I think, yeah. There it is. Number theory. Fun stuff. NPR, NCR. And you could just click whatever you need and it pops up. Obviously, I don't need it there because I'd already typed what I needed there. But there it is. So functions, and scroll down to the bottom. So let's keep moving with the worksheet. And by worksheet, I mean fun sheet. Mr. Peters' class has 4 freshmen, 12 sophomores, 3 juniors. How many different groups of 4 sophomores are possible for a project? Let's suppose he's going to put them together to work. And he wants 4 sophomores out of 12 sophomores, okay? Large group made smaller. Well, let me talk about what's insignificant here. We don't need to know how many juniors there are. We don't need to know how many freshmen there are. That's not important. It's just sophomores because that's all they're asking about. But it is a large group made smaller, and they never ranked everybody or ranked anybody. So this is also a combination. So in CR 12, 4, that is the ugliest 12 I've ever written in my life. But that's okay. We'll go with it. So here goes. In CR and then 12, 4. And there's a formula that actually figures this out. It involves factorial and division. It's wonderful. I love it. I would love to teach it to you, but not in this video. So sorry. 495. Actually, the formula makes a whole lot of sense if you think about it. Like when you see the formula and you realize the structure of it, and it's, math is a beautiful thing. Makes me almost cry. All right, Mr. Peters' mathematics class consists of 4 freshmen. I'm reading the next problem, by the way. 4 freshmen, 12 sophomores, and 3 juniors. He must choose 3 sophomores with the highest grades for a math competition ranked. Oh my goodness. Okay, here goes. Sophomores. So again, I'm only dealing with sophomores, so I don't need the freshmen in this problem. I don't need the juniors in this problem. I just need the sophomores, and I am ranking them from highest to lowest. So if we flip this paper over, we'll realize there's a large group put into a smaller group, and the order is important. Use a permutation, put the large number first. This one is a permutation, not a combination. So we're going to have in PR, National Public Radio, 12, 3, there it is. And if you really care, and you probably don't, but if you really care, I could do it more than one way. So let me clear out what I have here just so it doesn't clutter my screen. I'll keep this floating head where it is. In PR, 12, 3, and I get 1,320. So 1,320 different ways that Mr. Peters could choose 3 sophomores from the 12, and they be ranked in the top 3. However, let me show you another way. If I'm going to rank the top 3, check this out. I would have 12 options for the first person, times 11 options for the second person, times 10 options for the third. What? Same answer. This is amazing. Are your socks still on? Because that knocked my socks off. All right. Number 7, a pizza shop. It has available toppings of pepperoni, olives, peppers, bacon, olives. Wait, I read olives twice, but it was really onions. Wow. I'm actually hungry. I haven't had supper yet. Pepperoni, onions, peppers, bacon, olives, sausage, mushrooms, anchovies. How many different ways can a pizza be made with 4 toppings? Let's find out. Oh, wait. 4 toppings out of how many? Let's count. 8. 1, 2, 3, 4, 5, 6, 7, 8 toppings. It is a big group made smaller. Does the order matter? Does anyone ever, let me look you in the eye. Does anyone ever order a pizza and say, my anchovies are over the onions when it should be onions over anchovies? Like, no one does that. So no, the order does not matter in this case. So because the order doesn't matter, we are looking at, wait for it, large group made smaller, order doesn't matter, combination. So this is going to be in CR, and this is the newer way we do it because of Desmos. But again, the older notation is a little bit different in the calculator. So 8, 4, and we'll type that in. I'm going to use calculator on this one just so I don't keep going back and forth. So math, probability in CR, 8, 4. This is the notation that was used. 70. I call it the old notation. It's not that old. Chess club at Reynolds High School must select a president and vice president. Okay, let's pause right there. That's 2 people, and they are ranked. One person is over the other one, right? There is the leader, and there's the assistant leader. If the team has 13 members, how many ways could the officers be chosen? Okay. We have 2 people being chosen out of 13. This is a permutation. So in PR, 13, 2, I'm actually going to do this one the old-fashioned way. I'm going to do 13 people could be president, and then 12 people could be vice president, and I can do 13 times 12, and I end up with 156. It is the same as if I do this. Let me prove it to you. Check this out. NPR, 13, 2, also the same as 13 times 12, which we knew was 156 anyway. Okay? All right, now things get crazy. In a running competition, that would be a foot race. You race your feet. First place, second place trophy will be given to the top 2 girls and the top 3 boys. 9 boys, 7 girls. How many different ways can the 5 medals possibly be given out? First place, second place. Okay, the order matters. The order is important. This one is a permutation, but we're going to have a permutation for the boys, and we're going to have a permutation for the girls. And so there are 9 boys. So in PR, I'm switching notations here. I'm using the Desmos notation. I'm using that, which is different than what we see here, but it's okay. Same idea. 9 boys, but I want the top 2 ranked. And then there are 7 girls, and I want the top 2 ranked. So I'm really going to have this one and then this one, and let's figure out what they are. So actually, I know this one. This one off the top of my head would be 9 times 8, which is 72. This would be 7 times 6, which would be 42. And then the final answer actually is these 2 multiplied together. If I have 72 options here and 42 options here, then I'll do 72 times 42 in my head. I'm kidding. I'm not doing that in my head. I'm typing it in the calculator off screen. I have 3,024 options. Let's do this last problem. A committee must be formed with 3 teachers and 5 students. There's 8 teachers to choose from. That's a small school. And 20 students. That's a small school. How many different ways could the committee be made? Maybe that's not the whole school. Either way, here we go. We're going to have 2 different categories. We're going to have teachers. We're going to have students. And the committee does not rank people. Notice they never said first place, second place, president, vice president. So the order does not matter. This is in CR for both of them. Let's see, 8, 3 and 20, 5. Here's where the numbers come from. I had 8 teachers. I wanted 3. I had 20 students. I wanted 5. So we're going to do an NCR on both of those. So I am going to switch to Desmos very quickly and get both of those numbers and then multiply them together. So whatever I get here and here, I'll multiply my options together. So there's that big awkward floating head. There's actually a way to resize that. I think it's here. Oh, to make it even bigger and more awkward. Let's not. All right, NCR 8, 3 56. There we go. And I just checked it out, but I didn't. In CR, and then 20 comma 5, and that one's a little bit bigger. And I have 15504. So 56 is the first one, and then 15504 is the second one. So 56 times 15504, and I'll multiply those together, and I'll get something. Let's find out what it is. 56 times 15,504. I have 868,224, and I have written it on my paper. There it is. We multiply our options together. So I hope this makes sense. When in doubt, look back at your chart. Look at the flow chart. It's going to help you out a lot. There we go.